Mercy ma'am, I think we can start. Mercy ma'am.
Yes, sir.
I think we can start, ma'am.
Yes, sir. We'll start. Okay. A very good afternoon to all. I am Dr. Mercy, Head of the Department of Mathematics. I welcome you all to the one-day international webinar on basis of image processing and its mathematical insights, organized by the Global Journal of Applied. I invite Fr.L.Anish, Assistant Professor of Department of Computer Science, to invoke God's presence among us.
In the name of the Father, and of the Son, and of the Holy Spirit. Amen. God the Father, the unfailing light and the fountain of enlightenment, we pray and seek for creative and stable energy and disposition to trust you more and find inspiration and motivation to acquire excellence in academic performance and life. Star of student will go for greater things through education. We thank you for this opportunity to stretch students' understanding through their webinar, online learning, and the significance of image processing and its mathematical insight, hosted by the Departments of Computer Science and Maths in our university. Enrich the united and academic spirit of the two departments to organize henceforth such programs to unfold source of ways and means to support students' online learning. Continue to bless the university management to offer such useful program to occupy the students to join in the global effort to create responsible and educated students for generating a better world. We make this prayer through Jesus Christ, the mighty name. Amen. Saint Joseph, pray for us. In the name of the Father, and of the Son, and of the Holy Spirit. Amen.
Thank you, Father, for the invocation. Now, I would like to call upon Dr. S. Pradeep Kumar, Head of the Department of Computer Science, to give the welcome speech and to intro the chief guest.
very good afternoon to all. Respected Vice Chancellor Dr. T. Nanadurai, respected Register Dr. J. Robert Edwin Chester, respected Dean of Academics Dr. R.K. Behera, respected Dean of Student Affairs Dr. Charles, respected members of the management, HODs and staff members. A very good afternoon to all gathered here. On behalf of St. Joseph University Nagaland, I take the pleasure of warmly inviting all the participants who have come across from continents, countries, and from the length and breadth of this country to entrench themselves with knowledge by means of this webinar. The Global Journal of Applied Engineering in Computer Science and Mathematics is a biannual journal which was inceptionalized jointly by the Department of Computer Science and Mathematics for the sole purpose of publishing quality peer-reviewed research works in the combined field of mathematics and computer science. Mathematics is the foundation and cornerstone of almost all engineering disciplines. One such engineering discipline which was entirely shaped by mathematics is computer science. Computing devices started the origins as humble calculators which aided calculations and over the years evolved to do powerful calculations and helped humanity achieve many potent milestones like the infamous moon landing. It's true to say that computer science as a field wouldn't have been developed if it weren't for sound mathematical principles. All computer algorithms and programs are an offshoot of mathematical models and principles. Even today, the trust areas of computer science like artificial intelligence, machine learning, deep learning, data science, etc. depend heavily on the sound mathematical principles of linear equations, statistics, probability, fuzzy logic, etc. to name a few. One such field that is gaining prominence in computer science is image processing. At the outset, we can tell image processing as a computer code or software trying to process an image like a human. However, it's not easy as it sounds. There are sound principles and mathematical concepts to aid the same. To get clarity over these concepts and enlighten the mind of the researchers and students alike, the Journal House is conducting this one-day international webinar on the basis of image processing and its mathematical insights. Here have two eminent resource persons in our midst to shed light on this interesting field. To start up, Dr. S. T. Deepa, Associate Professor and Research Director from Sri Sankara Subrabai Shanum Jain College for Women, Chennai, Tamil Nadu, will take us through the topic of computational image processing. Here, the basis of image processing will be covered thoroughly. She obtained her PhD from Mother Teresa University, Kodaikanal, Tamil Nadu, and has over 17 years of teaching experience. Over the years, she has served in various capacities as heads and directors. She has published and presented around 30 papers in various national and international seminars. Most notably, she has been invited to talk shows such as Dial Jaya TV and has given keynote speeches in seminars hosted by various colleges and institutes. Further, to dwell into the mathematical principles surrounding image processing, Dr. V. Thangaraj, retired director and head, Ramanujan Institute for Advanced Study in Mathematics, Chennai, Tamil Nadu, will take us through the topic transformation techniques in image processing. He is an academician with over 30 years of experience in both teaching and research and has held many notable positions in his illustrious career. He served as a member of the study team visit to CIS countries for implementing the E-Network project and also served as a consultant for tele-education program of Ministry of External Affairs, Government of India. He acted as the coordinator Pan-African Network Project, Ministry of External Affairs, Government of India at Institute of Distance Education, University of Madras, and won the appreciation for the same from the Ministry of External Affairs and Telecommunication. He also served as the director and head from Ramanujan Institute of University of Madras. He has served as COE and many notable professions over the years. He has published over 60 papers and authored several books in his illustrious career. We, the chief editors of Global Journal of Applied Engineering and Computer Science and Mathematics, are really proud to have you both in our midst to entrench the participants in this vast knowledge, to dwell in your knowledge of image processing. Once again, I welcome all of you and have one entrenching section ahead. Thank you.
Thank you, sir. I request our Honorable Dean of Academic, Dr. R.K. Behera, to deliver special address.
Good afternoon, good morning, and good evening. continent you are. I welcome you, all of you, to one day international webinar on basics of image processing and its mathematical insights. I am extremely happy that the Department of Mathematics and Computer Science, St. Joseph University has organized this webinar, which is the need of the hour. Image processing is a method to perform some operations on an image in order to get an enhanced image or to extract some useful information from it. It is a type of signal processing in which input is an image and output may be image or characteristics, features associated with that image. Image processing basically includes importing the image via image acquisition tools, analyzing and manipulating the image and output in which result can be altered into image or report that is based on image analysis. Digital image processing consists of the manipulation of images using digital computers. Its use has been increasing exponentially in the last decades. Its application range from medicine to entertainment, passing by geological processing and remote sensing. Multimedia systems, one of the pillars of the modern information society, rely heavily on digital image processing. The discipline of digital image processing is a vast one, encompassing digital signal processing technique as well as technique that are specific to image. Today, I am happy that there are two prominent and dynamic resource persons like Dr. St. Deepa and Dr. V. Thangaraj who will present their ideas on this. It will be a new dimension to all. My special thanks to both the department for their global mathematics all. Thank you.
Thank you, sir, for your kind and encouraging words.
So now we'll start the session. The first session will be covered by Dr. St. Deepa ma'am. For the convenience of everyone, I request all the participants to kindly keep their mics mute. Those who have any queries can post it in the chat window, and those who are viewing it on YouTube, you can also put your any queries in the chat window, and the presenters will answer it towards the Q&A section. So as you all know, image processing is a very dynamic field. It has a lot of concepts, and it's a evolving application. With the aid of AI, it is now so prominent. So I welcome Dr. S. Deepa ma'am to take over the session to present a topic. Now, ma'am, please.
Yes, sir. Am I audible, sir?
Yes, ma'am, you're audible.
Yes, ma'am. Yes, ma'am.
Clearly delighted to be a resource person along with him today. Thank you so much, sir. And as the title says, like what I am going to deal with is very basics of image processing. I understand it is the people who are here are from multiple domains, from mathematics as well as from computer science. So I'll be starting from the very basic of image processing. Give me a minute to share my content. Is my content visible?
Yes, ma'am.
Yes, ma'am. Yes, ma'am. It's visible.
It is visible.
Okay. I shall start with the basics of image processing. So these are the contents we are going to see. The first one is like, to start with, we have to know what is the difference between your image and digital image. A digital image is actually a representation of two-dimensional image with digital values. As we all know, the digital values are represented as zeros and ones. So, the complexity starts there because we take a lot of colors and everything has to be represented in zeros and ones. So the complexity of the image processing start from the very representation of digital image. Okay, so what is this digital image processing focused on? It focuses on two important things. One is the improvement of the information which is available. The next one is processing of data for transmission and some other process. Let me explain that with an example. When I say an improvement of pictorial information, we are very aware that the old photographs can be processed and color can be added into it and it can be restored. Those are the things which comes under improvement of pictorial representation. But when I talk about processing of imaging data, it is processing of image data, something like stenography, where we include cryptography and image together and try to understand, encrypt and decrypt the data. So our digital image processing focus on two major tasks. One is improving the content which is available with us, and the second one is, with the content, what can I find? What new data I can find for the enhancement of my research and for the better representation. Okay, this is how we classify the processing. We classify the processing as low-level process, middle-level process, and high-level process. So the input of low-level process, input and output of low-level processes are images. Whereas when I talk about middle level process, where we divide the pictures into segments, we find the region and boundaries of this picture, then the input is image, whereas the output is attributes. Attributes can be what are the neighbors of a particular pixel, what is the region of that pixel, in which segment that pixel belongs to. Okay, so this is the middle level process. The high level process is from the output, from the input given, what I understand. No, it is something like image interpretation. Okay, so that is three level of process: low level, mid level, and high level process. And these are the different stages of image processing. So we are going to discuss all these things in detail. Image acquisition is a very basic process because we are going to deal with image. We need an image. Okay, image acquisition, then enhancement, restoring of image, morphological processing, segmentation of image, object recognition, representation of image, and image compression and color image processing. These are the different stages of image processing. So first we will start with image acquisition. We need a camera or a lens which will input the image and which will produce the image for us. Okay, that is the image acquisition. The first process is we have to get the image from through our lens and store it as a digitized image. That is image acquisition. The next one is image enhancement. See, we capture an image for a purpose. So depending on the purpose, I can enhance, I can restore I can enhance the details needed. We may need a minute pixel details. In that case, I will enhance the details depending on the attribute which is of interest to me. The next one is image restoration. From the distorted image, we are going to restore the image as much as possible. That is the restoration of image. Morphological processing is identifying the individual attributes and find the sensible data. That is morphological processing. So once the data is found, I can classify the data according to a certain criteria. That is called segmentation. And then from that, I will identify the object. I will try to identify the object, that is object recognition. Then I will restore and represent that in the way which I need. Then I will compress using a compressing software. Then I will generate my color image processing, the color image which is needed. Okay. So as such, image processing, we capture an image, we will bring that to a digital image, which is a binary image. We can even call it as a grayscale image. And then that image is again processed, but the output image will be a color processed one. This is a general thing which every translator do. You would have studied, translator, a compiler, which will convert the data into data which is understandable by the machine, then restore the data which is understandable by the user. The same thing happens here also. The image is first transferred to machine understandable format, and once the processing is done, again it is reflected, outputted as the user understandable format. Okay, so what are the different components we need in the image processing system? There are a lot of components which we need. The first one is image sensor. So there are two elements which is need to acquire the digital images. The first is the physical device, which is sensitive to the energy radiation, that is called a sensor. And the second one is digitizer. So we sense the data and we create an image, and that image will be converted into digitized image. So image sensor will have two things. One is image, sensing the image. The next one is digitizing, that is converting the image into a binary representation. So we have the specialized image processing hardware. These kind of hardwares, we call it as a front-end subsystem also. It is every unit will perform functions which require fast data throughput, because we capture data with a high speed, and with the same speed it has to be processed. So there are a lot of primitive basic operations, and there are complex operations also. So our CPU will be enhanced to work on this digital images. And we definitely need a computer which is with a good hardware, because when we store an image, there are two things required. One, storage space is more, so your memory should be efficient. Two, the processing speed is also more. Say, for example, you have a image which is a two-dimensional image. So the two-dimensional image in general will be represented as a matrix. So it can, minimum it can be a 722 by 722 pixels. So it has to be processed in a fraction of seconds, such that the user feels that the work is getting faster. Okay, so you should have a computer which is really efficient to handle images and videos. Videos, again, we can divide the videos into frames. So frames of images. So we should have a computer which is high-end computer. And we should have a special image processing software. In general, when we talk about research in image processing, we normally use MATLAB. We use Skylab, which is an open software. MATLAB is a paid one. Okay. So again, the volume, the size of the software access is huge. So the memory should be such that the software is also loaded, and executing the software will also be done in the less time. That is what I was telling. We need a mass storage capability, where every size, I was telling about 720 into 720, it can be 1024 into 1024. As we all know, 1024 is 1K. So to store an image, we need at least 1K into 1K memory space. Okay. So this is for a black and white image, because I say if a pixel, if it is a black and white image, I represent it as either 0 or 1. Okay, so one memory space is enough to store 1 pixel data. Whereas if it is a color image, the complexity is increased. We will get into the color images also. And again, the master, we can even have an external storage, or we can have a cloud storage. Okay, and we should always, while working with digital image processing, it is always better we always have a backup every day. The next one is you should have a image display. The image display can be a normal monitor as we usually have. But if you're really working on a research area to understand the, all resolution imperfect, it is better that you have a very good resolution display. And we should have hard copy devices also to take a printout and see how efficient and how good the quality of our images are. So, see, nowadays it is not that we work individually as individually. We work as a team. So, when we work as a team, or we work as work in a funded project as a team, the data has to be shared among everything. Okay, we have a drive which can be accessed by everybody. In that case, the networking should also be in good quality, so that the accessing of image is easy. So I store an image that should be accessed by somebody else. So that only when the network is of good bandwidth, I can access the image easily. So these are the components which we needed for the image processing in the current state. Okay. Next, what we are going to see is few attributes of, I was telling about attributes. Depending upon the attributes, we can restore the images. Okay. So we will see certain attributes of pixels. The first attribute of pixel is neighbor. Okay. Every pixel, as I already told, will be represented in a matrix. Okay. So every matrix, and in matrix, we will have X and Y column. Okay, so we have P of XY. The neighbors can be, there are 8 neighbors. So P of XY, X minus 1Y, X plus 1Y, X, Y plus 1, X, Y minus 1. These are 4 immediate neighbors, and we have diagonal neighbors also, which are X minus 1, Y plus 1, X plus 1, Y minus 1, X minus 1, Y minus 1, and X plus 1, Y plus 1. So we usually use this 8 neighbor concept to enhance the work. Okay, so if you leave the diagonal neighbors, the effectiveness and the quality of the accessing the pixel will not be so good, because we are leaving 4 other neighbors. So it is preferable that we use the 8 neighbors. And adjacency, as we all know, we would have studied in matrix. Adjacency is the element which is adjacent to it. So for a pixel, all the neighbors are adjacent. So we can find the adjacency of all the pixels. But we have a mixed adjacency. This is actually a modification of 8 adjacency. This is introduced to eliminate the ambiguities that is often rise when 8 adjacency is used. See, in an example, we can see for 1, the adjacency, there are lines from 1, 1 and 1. But at the end, we have adjacency lines only from 2, 1, 2 and 1, 3. Then 2, 1, 2, 2 and finally it is 3, 1. So we remove the ambiguities of 8 adjacency. 8 adjacency is nothing but drawing a line of all these 8 neighbors. So what is the digital path? As such, if I want to explain in a very simple line with the digital image processing as such is a combination of graph theory and matrix computation. So if you are very clear about matrix computation and graph theory, then accessing the image and doing processing in the image will be easy. Okay, so what is the digital path? Digital path is from a pixel X to Y, sorry, pixel P with coordinate X comma Y to pixel Q is nothing but a continuous, it is adjacent. From from XY, I will go to X1, Y1, I will go to X and Y1, then I will go to X, finally S and T. If S and T and X and Y are same, then I will have a loop, which we usually call it as a cycle or a cycle in graph theory. Here we call it as a closed path or a loop. So connectivity, if there is a path between a pixel X and Y, I say that they are connected. Okay. So for any pixel P in S, the set of pixels that are connected to it in S is called a connected component of S. If it only has one connected component, then S is a connected set. Okay. They are talking about a set S. Okay, so in S, every element is connected, then the set itself is a connected set. Region and boundary. In general, we know the English meaning of region and boundary. Region is our axis and boundary is the outer space. Okay, the boundary, the technical term or a computer term of boundary, we call it as border or contour. And region as such is a connected set. And we have a different distance measure. We have Euclidean distance and chessboard distance and all. We will see the distance measures also. For any pixel P, Q and Z with coordinates X, Y, ST and WV, distance is like this. D of P comma Q is greater than 0 if D of P comma Q is equal to 0. If and only if P is equal to 0, which means XY is same as ST. Okay, they are represented as different variables, different attributes. In that case, the size will, if distance between P and Q and distance between Q and P are same, or if P comma Z is less than the distance between P and Q plus distance between Q and C, where Z is in between P and, Q is in between P and Z. So it is an intermediate pixel. Q is an intermediate pixel between P and Z. So what is an Euclidean distance? We have a formula, X minus S squared plus Y minus T squared. Again, it is to the power of 1 by 2. We have city block distance. Again, all these things are equations. Here we use D4 is nothing but a 4 adjacency, where we are not going to consider the diagonal neighbors. So X minus T plus Y minus T. And the next one is chessboard distance. Here, instead of 4 adjacency, we will consider the 8 adjacency, which is again the same concept, X minus S plus Y minus T, but here we are going to consider the maximum value. This is the chessboard distance. This is how we will calculate the chessboard distance. So there is an example. So this here it is less than 2 because the maximum value available in 2 is, in this image is only 2. So we are finding the maximum value. So the distance D8 will be either less than or equal to 2. Okay, we have DM, which is defined as the shortest M path between points. So here we will consider the neighbors also to find the distance of the distance between 2 pixels. So this is the example. We have a following arrangements of pixels, and P2 and P4 have the value 1. So obviously the distance measure will be either have value 0 or 1, because that is the 1 is the maximum value. This is again another example. Case 2 where P1 is equal to 1 and P3 is equal to 0. So we will have the path P, P1, P2 and P4. The next one is color image processing. Okay, so sorry. So next thing what we are going to see is color image processing, where we will be discussing about including the colors. Okay, when we are going to include the colors, as I have already explained, the complexity of the pixel representation increases because the pixel will have the value for each and every description. See, we have a basic primary colors R, G and B. So everything has to be represented. So the complexity of pixel representation will be increased. But we are left with no other choice than accessing the images in color. So why do we need color? Because the color is a powerful descriptor, because we can see different shades of the same tree when we take it in the color. But when we take the same tree, a picture of the same tree in black and white, we can see only the shades of grays. So the power, the color as such is the powerful descriptor. A human eye actually can discern thousands of colors and intensity. So we have to implement those thousands of colors in our system also. That is a great task for us. So this chromatic light span, we all know, we would have studied in physics. This is the visible, spectrum. So this is basic of colors. See, the color that human perceive in an object is the color reflected from the object. So we are working. I have some disturbances. I don't know from. Thank you. Okay, so what we are seeing is just a reflection of the object, but the primary source is light. So we are going to see about the physical quantity to describe the chromatic light source, radiance, illumination, and brightness. Only depending on this, the reflection will happen, because we are going to work on the reflection of the object. So the physical quantities of the chromatic light should be understood first of all. Then only we can choose the characteristics of the image, how the image should be. Okay, the first one is radiance, that is total amount of energy that flow from the light source. It is measured in watts. The next one is luminous. It is the amount of energy an observer perceives from the light source. So it is how the object absorbs the light source. We would have learned that black will absorb all the light source, and white will reflect everything. Okay, so this is luminous. We should know that basic concept also. The next one is brightness. It is subjective descriptor. It is actually really hard to measure, but it is an achromatic notation of intensity. So these are the basic characteristics or quantities to describe the chromatic light source. So we have primary and secondary colors. We all know primary colors, which is RGB. And this International Commission of Illumination defines the wavelength for the every primary color. Okay, the primary color is for blue is 435.8. For G, it is 546.1, and R, it is 700 nm. And everything will be called as RGB. We all know red, green and blue. But what is the secondary color? Secondary color is actually a subtractive color. So we will add green and blue, we get it into cyan, and red and green make it as yellow, and red and blue make it as magenta. So we will be working on primary and secondary colors. So this is the pictorial representation of primary and secondary colors. So this is the additive primary, which means adding red and green, we get yellow. This is subtractive primaries, where subtracting yellow from magenta, we lead it to red. Okay. So we have two primaries. One is additive primaries and subtractive primaries. So coming to the color models. Okay, so far what we have seen is the basic of images, which is basically represented as pixel, X and Y, okay, 2D images. And we started discussing about the color models. Okay, so the color models, we have different ways of representing the colors. Okay, what color model to use when depends on the applications. Okay, but basically we have 4 different types of color models: RGB color model, CYM color model, which is primary and secondary color models, CYMK color model, and HSI color model. So the first 3 will be suitable for hardware related applications, whereas HSI is used for human description. So if you are going to combine the image processing and artificial intelligence, it is better we go for HSI, because HSI is a model, is a way where human beings see the images. So this is the RGB model, which is through 3-dimensional representation. G in x-axis, red z-axis, and blue in y-axis, representing that. And they have, it is specified the secondary colors also. Blue and red together we get magenta, and blue and green together cyan, and blue and red and green together will get yellow. In between, we will have gray scales and black. So if we include black along with our secondary model, we end up with CMYK model. So this is actually used to generate hard copy output. So how can I get CMY? We have discussed already. 111 represents black. So if I'm going to subtract RGB from 111, I will end up with CMY, which is cyan, magenta and yellow. So this is the subtractive primaries. So I think this picture is self-explanatory. We have a black background. There above we have a red. If we subtract 1 from red, we will end up with C. So including black along with your secondary colors, we end up with CMY model. So initially representing images was done by RGB model. See, it is all a kind of technical advancement. Initially, we were using only black and white camera, then the camera with rolls, then now we have digital camera, where the choice is given to us to store a data or delete an image. Okay. So similarly, due to the advancement of technology and the software available, initially we represent everything in black and white. Then we used grayscale method. Then we used RGB. Advancement of RGB is CMY and CMYK. Then we thought, why can't we represent that with human ideas itself. This is how even the high-end softwares are evaluated. Initially, we used only machine language softwares, but when advancement come, people really felt difficult to use assembly language and machine level language program. So we started developing high level language program, which is very similar to our English language. Same here in image. We were using a technical term of RGB, CMY and all. Then we thought, why can't we have a human description of the color? Okay, so they come up with a model called HSI model, which is hue, saturation, and brightness. Okay, again here brightness is a subjective descriptor. It depends on the source of light. The next one is hue. It is the color attribute that describes the pure color. Saturation is from the pure color, how it has been diluted. So saturation is the measure of the degree to which a pure color is diluted by white. Okay, so you have a red, add white. The quantity of white added, the percentage of white added is saturation. Whereas the basic color is here, hue. And brightness is a subjective descriptor which depends on the source of light. So as we have discussed earlier, RGB is useful for hardware implementation and is related to the way in which the human visual system works. Well, it is not an intuitive way, because if you can understand, see, RGB combination has less number of colors. Whereas if you use HSI model, the number of colors and generation of colors will be more. So when I say RGB is color generation and HSI is the representation of colors. So again, we have another thing called intensity. Intensity is actually the brightness measure, because it is so, brightness cannot be measured because it is subjective. We use the concept called intensity. Okay, so here intensity can be seen in grayscale images. So there will be variation in grayscales depending on the intensity of the image. So this is the HSI component of the image. We have a RGB image. If it is only Q is done, then the representation is given in the top right corner. Intensity is measured in bottom line, and we have saturation. So saturation, as we know, is how much the content, image content is diluted with the presence of white color. Okay, so that is called saturation. If you see in the RGB, the center portion is full of white. So the saturation is 0. So if you see in the saturation column, that is fully black. So now, as we understand, using HSI model is also helpful for us. We can convert the RGB model into HSI and HSI into RGB model also. So this is a formula given. So RGB, its HSI values are calculated like this: H is equal to theta or 360 minus theta if B is less than G, and B if it is H is equal to theta if B is less than or equal to G. It is 360 minus theta if B is greater than G. So it is the combination of blue and green. The H is calculated using the combination of blue and green. Okay, and S is calculated. We are going to calculate the cos inverse, and S is calculated including all the three colors R, G and B, which here we will consider the minimum value of RGB. Which value contributes less? That is taken for saturation, because saturation is all about dilution of color. So we will take the minimum value of the RGB. And intensity is nothing but the average of all the three colors. So this is vice versa, converting HSI to RGB. So here we are dividing the session into two things. One, RG sector. Three things: RG sector, GB sector, and BR sector. Okay, the degree is first 0 to 120 degree is RG sector, which is contributed by red and green. 120 to 240 is contributed by green and blue, whereas 240 to 360 is contributed by blue and red. And the formulas are given. So here blue and R sector is contributed by is between the angle 240 to 240 degree to 360 degree when it comes to Q. So Q has a value from 0 to 360. So first sector, first block is done taken care of by RG, which is red and green. Then GB 120 to 240 is GB, which is green and blue. Then 240 to 360 is BR, which is blue and red. Pseudo color image processing. Pseudo color is, as we all know, pseudo is virtual. Okay, so we are going to do a virtual color image processing. So here what we are going to do is we are going to assign colors to gray values based on certain criteria. The criteria can be intensity also. Okay, so then we will interpret the human, we will interpret the image depending on the grayscale events. Why do we need this pseudo color image processing is, as I've already told, only binary values can be understood by the machine. So we have to, all said and done, the input to the computer should go as only zeros and ones. So it is always better we convert that between values zeros and ones. So that is where the grayscale lies, between the values zeros and 0 and 1. And we will have the gray colors to color transformation also. This also I have discussed because machine understand only black and white. So I can give any value between black and white, that is grayscale. But I as a user would love to see a multitude of colors. So there should be an option to convert from the color image to the grayscale and the grayscale image to the color image also. So this is introducing gray color. Pseudo color is virtual or false color. This is how we are going to introduce the pseudo color, where we convert the data into a grayscale image. So let us see about intensity slicing also. So here, as the name implies, we are going to divide and or categorize the intensities. Okay, depending on the intensity, we are going to categorize the pixels. Okay, so these in pseudo color image processing, depending on the intensity, we will divide the colors and allot the corresponding gray color. Okay, so first we consider an image as 3D function mapping spatial coordinates. So now XY is converted into XYZ, and there will be a plane which is called an intensity plane. So that intensity plane will divide the pixels into two segments. So then we will convert that into a different grayscale. So we will place the but we have to place the plane. Depending on the placement of the plane, the color differs. Okay, so this has to be designed in which intensity I have to place my intensity plane. Okay, so if the plane is divided, one side of the plane is converted into another grayscale, and the other side will be converted into a lesser or a brighter grayscale. Okay, this is the example of intensity slicing. This is a slicing plane. Okay, this is my image. I am slicing it. So whatever comes above will be in a different grayscale, and whatever that goes below will be in the lighter grayscale. So this is one of the pseudo color image processing. So there are certain applications which is testing of, mostly it is done in the medical field, radiation testing, X-ray. Those things can be done using this pseudo color image processing. So it is actually the picture of a weld, where we keep, connect two wires or any two objects, welding. So that is an X-ray of a weld image, which is, you can see the different, variation of grayscales, and that is converted into a color image. Statistics of rainfall, grayscale, and the pseudo color image. So how am I going to convert grayscale into color transformation? So we have a transformation element for everything, a function. F of R is red transformation function. F of G is green transformation function. F of B is blue transformation function. Okay, depending on, we use all the three functions to convert a grayscale image into the color image. So as I've already told, the pixel representation, when it is represented as a color pixel, will have a lot of complex data involved. So see, we initially the pixel is represented as only X and Y. Now I have to include the R value of X and Y, G value of X and Y, B value of X and Y. So in general, if you see, there are 6 values. So in black and white, we stored only one value. Sorry, 2 values, one for X and one for Y. Here we have 6 values, 3 for X and 3 for Y. This is for a 2D image. Again, if you are going to go for a 3D image, you will have a 3 value of Z also. So how am I going to deal with color vector? Okay, so here we have per color component processing, which means I am going to process each and every color. We have seen functions F of R, F of G, and F of B for all the colors. So that is one way. The next one is vector based processing, which means we will process the color vector for each pixel. Okay, so how can I represent color vector? Again, every pixel is a representation as a matrix. So each color will represent as an individual array. So array can be represented as a color vector. So when can these above methods be equivalent? It can be applied in both the scalar and vector values. So it is independent of each and every color components. So there are 2 spatial processing categories. If you see, when we are working with pseudo color processing, we are going to represent that in the spatial area. Okay, so how am I going to represent that spatial data? So I have 2 ways. One is pixel wise processing and neighborhood processing. Then your color transformation from grayscale to your color image, where we use the individual color function of R, G, and B. So which color model to be used? As I've already discussed, HSI is better because it is very much similar to the human representation. But if it is a hardware implementation, it is always better we go for RGB. So how to modify the intensity of the color? I can use the function S3 is equal to KR3, the transformation of HSI request complex operations. So K is a value which is between 0 and 1. Why am I going to use 0 and 1? Because 0 is black and 1 is white. So to convert into a grayscale, we should always have a value between 0 and 1. So depending on the intensity of black or saturation of white, I can increase and decrease the value of K. The K, same color modification in CMY color space. So this is how the representation changes. This is the actual picture when the intensity is reduced or the brightness is reduced. This comes to the second picture. When I'm going to consider only the cyan component, when I'm going to, this is the integer color component. The full color picture is here, and we are considering the individual picture component. I am taking CMYK model, and I am taking RGBN model, and I am considering the HSI model also. So all the models are implemented in one particular image, and these are the different outputs. So what is the problem using the cube?
Ma'am, we can't hear you.
Deepa ma'am, can you hear us?
Ma'am, it's not audible.
It seems ma'am's network is down. All of you kindly wait for another 5 minutes. சரி நான் அந்த ஒன்றை கட் பண்ணிடுறேன். நான் அவளை கட் பண்ணுறேன். இப்போ உடனே பண்ண சொல்லுங்கள். எவனா இருக்குங்களா?
I left the meeting. I don't know that I left the meeting because I was in my presentation mode. Let me present the content again.
You can represent, ma'am, no problem.
Yes. I just want to ask you, like, how far I was audible to you, like, till this slide. Because I don't know when I left.
The previous slide, ma'am.
This, sir?
Yes, ma'am.
Is this a use which color model and transformation? Is it, sir?
Yes, ma'am.
Okay. Okay.
74th slide, ma'am. Slide number 74.
Okay. So I think then this is the 74th slide, sir.
Yeah.
Okay. So what is the problem with the Q component is because, there is a discontinuity in the red color because red color contribute more to Q. So there is a discontinuity. So obviously the representation, if you are going to represent that in the grayscale, the discontinuity still exists, and there may be the effectiveness of the output will not be that much. So this is how the we are going to represent the slicing. The slicing. So when it comes to slicing, all that matters is depending on the finding the slicing plane. So we can take two different types of regions. Region, as we all know, is the area of interest. So I can consider either a sphere region or a cube region. Depending on the region selected, the output also differs. So this is the cube representation and the sphere representation of the full color image. So if we have seen this output also having a different representation of considering only a primary component or only one component of interest. So from all this, what we can understand is this image processing, it depends on the application. So what information I need is should be first identified, and depending on that, I can identify the representation of the images or representation of the region. So this is smoothing of the image, which can happen using vector processing or pre-component processing. So this is a very renowned peak of image processing. So we have original image. If I'm going to consider only R, G, and B, where I'm considering Q saturation and intensity. So here I am going to smoothen that with intensity. So I will use the value of smoothening mask for intensity, and I will get the output. So now computational imaging. This computational imaging is nothing but where we are going to use it in a real time. It is actually getting faster and cheaper, and we have we work on we cannot work on reflect some radiations. So here we are going to code that image processing. So all what we have seen is the basic of computation imaging. And there are few examples of computational imaging, which is synthetic aperture imaging and coded aperture imaging. In general, I think we all know what is aperture. It's just an exposure to your lens. As we all know, that is one of the first step of image processing, that is image acquisition. So there we have to acquire the image. That can be done only by sensor as well as digitizer. So the sensing, how exposed the lens of the camera is this is the aperture, and we have synthetic aperture imaging and coded aperture imaging. Diaphanography is nothing but working on the cancer cell images, and cone beam reconstruction. So there are two traditional approach and new approach also. One is coupling of resolutions and precision imaging, the traditional approach. New approach is precision illumination, where we are going to just consider the opposite of precision imaging, and then we will have multiple images where we convert the background as different textures. And these are the references that I have made. Thank you so much.
Thank you, ma'am, for your wonderful time. It was really a very interesting section. Some of the participants have posted questions, ma'am. Manoj Chandar is asking, is it possible to do image processing with color image or only with black and white image or grayscale images? Also,
sir,
to make a mask.
Yeah. See, let me answer the first question. Like the grayscale image has to be identified because the binary values can only be understandable by the machine. So the first thing is converting any color image into grayscale image. So it is always mandatory to work with the grayscale image. So how to make masks? Somebody has Manoj Chandaran has posted in the chat. A mask is nothing but a matrix. Okay, depending on the values, see matrix, we have the values of R, G, and B. R, G, and B. So automatically, see if you are interested in the value of R, you have to mask the remains. It is nothing but an AND operation in digital processing. So masking whatever you don't want, you mark those columns as 0. Whatever you want, you will mark those columns as 1. So when you have a AND operation between the existing image and your mask, what data is needed, we will get. That is called masking, which is basically masking is nothing but an AND operation in digital processing.
Then Renbitan, a person named Renbitan ma'am has asked, what is the best algorithm for human face recognition regardless of race that they are in?
Sir, I couldn't understand.
No, he's asking actually, is it possible to recognize human faces despite any race, that is color of the skin?
Yes, sir, we can always we can always recognize the human face. Probably the probability is almost 95 to 99% of identifying the same images. Now we have lot of neural network algorithms and artificial intelligence algorithms which can be implemented to identify and recognize the face.
Ma'am, Prakash Mukherjee is asking, is it possible to transform 2D images to 3D?
Sir, everything is possible when we include it in computation, sir. But transferring a 2D image into 3D image, we may not get any effective and effective output, sir. So flattening of the image can enhance the output. But widening of an image, again, we are widening the the spectrum. So obviously the output is vague. But when you restrict it, converting 3D into 2D, we are just giving coming from general to specific domain. So obviously the output will be more. So though it is we can do it, but it is not recommended.
Then Shambhavi Jasa is asking, ma'am, can you elaborate about image processing in astronomy?
Image processing in astronomy, we can as weather forecasting, we can always work on the satellite image processing. Basically, finding the satellite image processing data is difficult. But we can work on satellite image processing to predict weather, climate, everything. Okay, and there are a lot of algorithms, and the best algorithm, as I have told, anything when it comes to image processing as of now, the best algorithm you can use is fuzzy logic, your neural networks, and artificial intelligence.
Then we have one more question, ma'am. While transferring from color to image, from color image, is there any chance of loss of information?
As such, no, sir. But whenever we, because 0 to 1 has a value from the grayscale value also. 0 is black and 1 is white, and we have grayscales. As such, no, we have lot of effective algorithms which can restore the black and white images into color images. So, as such, there is no loss of information because those effective algorithms are available in the image processing. There are predefined, image restoration algorithms in MATLAB and Skylab itself.
Dr. K.M. Rupa is asking, losing original features, ma'am, when converting 2D to 3D and 3D to 2D.
Yes, sir, that is possible because 3D we have a lot of data. That data is, see, it is something like representing a 3 by 3 matrix into 2 by 2 matrix. So obviously we will lose data, or else we should find an effective algorithm which can represent 3 by 3 into 2 by 2.
Anybody have any queries can ask. Mercy ma'am, is there any query from the YouTube section? Mercy ma'am?
No queries, sir. No queries.
Then shall we move to the second section? Mercy ma'am?
Yes, sir.
Sir is available, right?
Yes, sir.
And Deepa ma'am, thank you very much for your intriguing session. Now we shall move to the second session by Dr. Dr. V. Tangaraj sir, who is the retired director and head for Ramanujan Institute for Advanced Study in Mathematics. As I told you in the introduction itself, image processing is nothing without any mathematical principles. So one of the main mathematical principles that is normally used is transforms. So sir has agreed to take us through this mathematical concept. Sir, I now give you the time to start your presentation, sir. So I think you have to unmute your mic, sir.
Hello.
Yes, sir, we can hear you, sir.
Can you able to see?
Yeah, we
Yes,
are able
sir.
to see, sir.
Huh?
Yeah, we are
Yes,
able
sir.
to see, sir.
Are you seeing that the borders and everything
Yeah, yeah, it's visible, sir.
visible?
Yeah.
Okay. Okay. At the outset, I thank the organizers for inviting me to give a talk on some transformation techniques in image processing. I think morning we had Dr. Deepa has presented how the image processing involves so many stages, so many techniques. But before understanding the image processing, I would like to give you mathematical ideas behind this image processing. I am not going to talk about the computer science point of view, but here I will take primitives, and these primitives how to recover, how to convert. And these are the things that I want to show, for which how mathematics is useful. This is what we are doing. I am going to tell you. In fact, these the topic which I am going to tell you are well known to people who are working in mathematics department. And for computer science department also, they may be very familiar with it if they are using it. Anyhow, as a compromise, I make it as simple as possible without going a lot of mathematical derivations into this. Yeah. I think this is my request.
I think she has already given the definition for what is an image. An image is a spatial representation of. There is some noise problem. Yeah.
No, sir.
Okay. An image is a spatial representation of a two-dimensional or three-dimensional scene. An image is an array or a matrix, pixels, picture elements, arranged in columns and rows. Digital image processing. Why? Interest in digital image processing method stems from two principal application areas. One is improvement of pictorial information for human interpretation. Next one is the processing of image data for storage, transmission, and representation. Right. What do you mean by a digital image? Already she has given the definition. An image may be defined as a two-dimensional function, f of x comma y, where x and y are spatial or plane coordinates, and the amplitude of f at any pair of points x, y is called intensity or gray level of the image at that point. She has already explained intensity and the gray level, how these gray levels are converted into digital image using zeros and ones. Digital image, when x and y and the digital values of f are all finite discrete quantities, we call the image a digital image. Now she talked about this same thing. F of xy is RGJ, red, green, blue. The field of digital image processing refers to processing digital image by means of digital computer. Now, we take the original image, call it GXY. First, you discretize this because these x and y are continuous variables. Now we are discretizing it. When it is discretized, it is I and j are integer values. Quantization Fij, and this will become digital image. So the original image, now we want to store it in the computer, it will become Fij. The choice of the particular transform in a given application depends on the amount of reconstruction error that may be tolerated and the computation sources available. In fact, somebody has raised, is there an error or 100% we can get back into? She was feeling that the proper use of software we can get back and other things. In spite of it, there is an error. Statistically speaking, the errors can be measured and then the errors can be minimized in such a way that we can get original image and approximately original image. Compression is achieved during the quantization of the transfer coefficients, not during the transformation step. This is a very important one. And here, there are so many mathematical tools are used in the image processing. I am going to take one or two only, if time permits. Image modeling or transformation is aimed at exploitation of the statistical characteristic of the image. What are the statistical characteristics? Correlation and redundancy. And here, look at this period, frequency, amplitude, phase. These are all the four fundamental primitive concepts. Now you have image like that. Here, first I will take this wave, and here it's a time axis and then voltage axis. Now this is called amplitude, and the t is the period, because when you started and you are again coming back to this, and this is called a period. And frequency is nothing but 1 by t is the frequency. Amplitude is this height is the amplitude. So these are all the, what is the period? Period means here the t. Frequency, 1 by t is frequency or 1 by f is period. And then amplitude and phase. Look at this. Now, suppose this is A, B, C, D is the 4 points. This time axis and instantaneous amplitude. How this, what is the amplitude for A, B, C, D? Now look at this. A is 0. For this B it is 90. For this C it is 180. For this D is 270. So So this is how the measure angles are measured in the anti-clockwise direction. Okay, this is the phases of ABCD of sine function curve. Sinusoid. Yeah. Now we want to talk about the Fourier transform, and we have that the transform technique. We have the Fourier series, Fourier transform, and I may talk about the wavelet transform. Only I'm going to take it up only three aspects. Of course, there are a Laplace transform and Z transform, and everything is there. Discrete cosine transform, then Walsh-Hadamard transform, wavelet transform. Now we'll talk about all the four things, and then what is the difference between these four types of transformation. For Fourier transform and discrete cosine transform basis, images are fixed. These are input independent and sinusoidal, that means cosine and sines in nature. Provides frequency view, provide frequency information, and the temporal information is lost in the transformation. WHT, I mean the third one, is non-sinusoidal in the name and easy to implement the frequency domain. Wavelet transformation, the word wavelet itself tells it is very small. See, what is the drawback with the Fourier transform? It is nullified by the wavelet transform, because in the when you focus on the small area, that Fourier transform may not work, but whereas that wavelet transform will work out very beautifully. That is the idea of introducing this wavelet concept. Fourier is good for periodic or stationary signals, I mean the Fourier series, but wavelet is good for transients, for non-stationary data. In fact, Fourier transform is also for non-stationary, whereas Fourier series is good for periodic and stationary. That is the main aspect of this talk. How when your image is represented in the form of a periodic function, how we going to convert into or how approximately we can near to that area original curve. That's what we want to see. That means I will see some diagrammatic representation. When you take that terms of the series, increase the number of terms in the series, how good we can approach the original wave. Now look at this Fourier transform. It is a time. I hope you can see that image. And this is a square image, and this frequency image is this Fourier transform. Okay, this is in terms of seconds, and this is in terms of hertz. This is the idea of Fourier transform. Actually, this this original curve is approximated by means of this. Introduction to Fourier transform. Virtually everything in the world can be described via waveform, a function of time, space, or some other variable. This is a very important notion. Everything in the world can be described via a waveform. If I am speaking means it is reaching your ears only through wave. How we want to represent it? That's what the Fourier did it. Fourier did it for periodic function and a non-periodic function. For periodic function, he has used the series form. For non-periodic function, he has used the Fourier transform. That is the basic difference. For instance, sound waves, electromagnetic fields, and elevation of a hill versus location, prices our favorite stock versus time, and then etc. These are all examples for waves. Fourier transform gives a unique and powerful way of viewing these waveforms. The purpose of this talk is to explain the following fundamental facts. What is the fundamental fact? One fundamental secret of the universe. All waveforms, no matter what you describe, or what you scribble or observe in the universe, are actually just in the sum of simple sine and cos curves with different frequencies. That is why in the Fourier series, you have cos terms and then cos function and the sine function. That means cosine function and the sine function. And then multiplied by each some weight. And the weight also had some interpretation. Why it is a very funny combination, where a cos function is an even function, sine function is an odd function. Why we are using cos function and sine function and the combination of these, and and this combination of this will give you approximate to the wave that we have in our mind or we observe. Decomposition of waveforms into sinusoids. Fourier transform decomposes a waveform into a real world waveform into sinusoids. That is, Fourier transform gives us another way to represent a waveform. Of course, the original will be there, and by Fourier transform you get another waveform. How far it is very close that you want to see, there will be some error will be there. And that error we want to minimize it. That is why you have so many algorithms. As an example, let us break up the waveform in figure 4 and the following into building blocks or constituent frequencies. This decomposition can be done with the Fourier transform or Fourier series for periodic waveform. Non-periodic will use Fourier transform. The first component, I think I will go to the next slide. The first component is sinusoidal wave with the period 2 pi. Now here, starting from this 2 pi. So that's what you see, it is represented here. It is 6.2 here, 2 times pi. And the amplitude is 0.3 as shown in figure. Now, here you have the original one. After transformation, you are getting this waveform. Okay? But it is not very close here. But we want to approximately to this curve by adding more and more terms in the Fourier series. Okay. The second frequency will have a period half as long as the first, twice the frequency. How? Yes, look at this. Now I have included more. And now this is your original. Blue one will be the original, and your transform will give you very nearest one. Okay, let us look at, we will increase that frequency. The third frequency component is 3 times the frequency of the first one. The sum of the first 3 components, now here, 1, 2, 3, and here you see you are approximately nearing to that by adding more and more terms there. Again, you increase this. Again, you will get, now I am writing separately. Now, this wave represented by means of this, by the transformation. 4 fundamental frequency curves. Okay, while this seems made up, is it true for all waves? This goes for TV signal, cell phone signal, sound waves that travel when you speak. This is what I was telling. In general, waveforms are not made up of discrete number of frequencies, but rather a continuous range of frequencies. That is an important observation. And this observation is tackled by the Fourier transform is a mathematical tool which shows the deconstruct the waveform into its sinusoidal components. This has multitude of applications. Aids in the understanding of the universe and just makes life much easier for the practicing engineer or scientist. Which one? This Fourier transform. That is why all engineering students are compulsorily studying this Fourier transform. And but engineering students' point of view, they will calculate the coefficients, Fourier coefficients. Given a function, they will calculate. Why they are calculating, why you want to calculate, all these things will have applications in the image process. Of course, that application part is missing in when we teach the Fourier transform in the M1 or M2 class. The Fourier series breaks down the periodic function into some of the sinusoidal functions. This is the first point you must note it. But the Fourier series works on periodic functions. If a Fourier transform for, Fourier transform for, sorry, it is not non-periodic functions. not periodic, non-periodic functions. To start with the analysis of Fourier series, let us define the periodic function. A function is said to be periodic with the fundamental period t if f of t plus capital T equal to f of t. That means the same behavior is repeated after time t or duration t. Suppose you take 2t, again it is f of t plus t equal to f of t plus 2t, like this. That is why it's called period. So you take only the fundamental period now. Period is t now. This means that the function of time with the period t will have the same value t seconds as it does now, no matter when you observe the function. See, this is a very important observation. Why we want to take this periodic function? For example, you take the first week behavior, the second week behavior, third week behavior, all are same. Therefore, the week duration is the fundamental period. That's what what we mean by periodic function. Note that a periodic function with the period t is also period with the 2t. Yes. So the fundamental period is t, that is greater than 0. That is the smallest possible t for which equation 1 is always true. What is equation 1? An example, look at the plot for the figure following figure 8. Look at this, t and t. This is called the square wave function. This square wave function has a fundamental period t. That means 0 to t. Here you are starting it, the same behavior, and you are letting it here. So the period is t here. Let us define the Fourier series now. Now, we have to consider two things now. One is a periodic function, another one is a Fourier series. The periodic function and the Fourier series, when they are going to be approximately same. It's not exactly, but approximately same. This is the entire Fourier series analysis goes only to finding out the different types of conditions by which you can approximate the periodic function by means of Fourier series. Now the Fourier series with the period t is an infinite sum of sinusoidal functions, that means cosine and sine, each with a frequency that is an integer multiple of 1 by t. Now here, look at this. And the inverse of the fundamental period, 1 by t, right? The Fourier series also includes a constant and hence can be written as, forget about this a naught. Now this an and bn, an times cosine and it's not an, it's a bn times sine 2 pi mt. Yeah. For an arbitrary periodic function is f of t, Fourier series is g of t. And g of t and f of t, how they are very close. How closely can we approximate this function with a simple sinusoid? That means using cosine and sine, each with a period, some integer multiple of the fundamental period. Why we are talking about, this is the workshop on or webinar on image processing, but we are talking about Fourier series because the fundamental thing is how the curves are approximated by known functions like a cos and sine theta. In mathematics, always right hand side is a known thing, left hand side is unknown. Left hand side is f of t, periodic function is given, and you want to approximate on the right hand side g of t using cosine and sines. That is the principle of equality. That is for a given period function, how closely can the function gt approximate f of t? It turns out that the answer is one of the coolest results in all of mathematics. And of course, there is some integrability condition is there. Integrability condition, I will tell you how under such condition alone you can proceed further. The whole mathematics of Fourier series lies there. That is, we can approximate f of t, I mean the periodic function, exactly whenever f of t is continuous and smooth. Smooth here means it is a differentiability condition. That's what we call it smooth here. In real life, of course, if you have a discontinuity in life, it is miserable. Therefore, in real life, we assume that all functions are continuous and smooth. So for the practicing engineer and the physicist, they will assume always continuous and smooth. All periodic functions can be exactly represented by Fourier series. This is the very beautiful answer available in mathematics. To find the Fourier coefficients, A0, AM, and Bn in equation 2, we see the following slides. To approximate a periodic function g of t with the fundamental period t with the Fourier series, sorry, this is f of t. Periodic function f of t, only the power series is g of t. What are the optimal Fourier coefficients am and bn? Am is nothing but the coefficient of cosine function. Bn is the coefficient of sine function. You have that cos function, multiply this cos function. If you have a Maple or MATLAB, you draw the curve for cos theta, then 2 cos theta, then 3 cos theta, and then also separately you say, draw figure for sin theta, 2 sin theta, 3 sin theta, 4 sin theta like this, and then you take the addition of this and then see what is the effect you have. That very beautifully you can visualize this using Maple or MATLAB. First, look at the one-term approximation. Now we go by one. First term is A0, G0, GT of t, the first term is constant. And that constant this constant A0, in Fourier series, some of the books, they will take A0 by 2. It is only for mathematical convenience we define A0 by 2 or A0. Doesn't matter. Okay. It's only mathematical convenience you are writing A by 2, but you will know what is that. Yeah. Here we have a one-term approximation for the function. For given a periodic function, and you have taken g of t equal to A0. What is the best value of A0 that we can choose in this case? Without proof having the optimal value of A0 equal to 1 by t, 0 to t, f of t dt. That means you are taking the average of, this nothing but average of the function, average value of the function. 0 to t, the length is t, therefore 1 by t. So this average value of f of t is taken to be A0. I think we can prove it. How do you go? How to get this? Well, to answer intuitively, the integral of the function over the period is a formal mathematical way of writing the average value. In fact, this average value, I think it is not far away. Now, let me give you some idea about some theorems. Graphically, I will, for example, you know A to B, some function f of x dx. We know that this is f of x is here, this is f of x. Suppose you take this is equal to A and this is equal to B, then this is given by this integral. But suppose this is divided by b minus a. This b minus a, that means you are taking the average value. So average value, how we can get it here? For example, this nothing but there must be some value C. Then when you draw the line and the area of this curve is equal to the area of this rectangle. Suppose this is equal to f of c, some point C. Actually, when you multiply this, the area is nothing but integral a to b f of x dx. This is nothing but b minus a into f of c. What is this? B minus a into f of c is nothing but a rectangle area. But whereas here it is area under the curve. Actually, what we have here is a beautiful problem. Two geometrical figures. One is area under the curve between A to B, Another one is area of a rectangle. How they are equal. That's what here says. There is this is called mean value theorem. The average value you can find is C such that this 1 minus the area under the curve is equivalent to this. This has given a very beautiful conjecture in mathematics. You know, take a square and take a circle. You take, for example, r equal to 1. So this is the value. What is the area? Area is pi. Can you have a square whose area is pi? That is the question. Can you have a square with area pi? So here also two geometrical figures. This is a very famous problem, namely squaring a circle. See, look at the connection. See, here the mean value theorem we can represent by means of through conjecture, namely squaring a circle. Squaring a circle is a unsolved problem in mathematics. Only Ramanujan has given a approximate solution in his notebook, Ramanujan notebook. You can see that if you have library, you go and then see that. In his notebook, you can see the proof of squaring a circle problem, but he has given a geometrical construction for this. Why I am telling this is, in what way it is relevant to our discussion is, now whenever two areas are equal under different conditions, now here the one mean value theorem gives an answer to this, but whereas this is an open problem, it is available in math. Okay, now why I am telling this? This mean value has got some interpretation A naught. Well, to answer this, the integral of the function over the period is a formal mathematical way of writing the average. Fine. So the first term in the Fourier series is a constant, and it is the average value of the function. Fantastic. That is the interpretation for A naught. Fine. Now look at this. The square waveform and one-term constant. This is the square waveform for which now we have, what is the, this square waveform in our Fourier series expansion, if it is equivalent to the constant means A naught. A naught is nothing but what? 0.5. For the square wave, where is the 0.5? Here is a point. Same thing here. Separately drawing this, you have the 0.5. So for the square wave function, the average value is 0.5. The average value of this function is 0.5. And the one-time expansion along the function is shown in the here. What is this? The 0.5. So that's equal. Let us take another. Take one more term. Say B1 term. So that now we have a two-term expansion for the Fourier series. A naught B1 sine 2 pi by t. Cos function we have not taken. We have taken the sine function. Why we have not taken? Because there is a reason for it. You take this plus A1 cos 2 pi by t, capital T. So now we are not taking this form, we are taking that the B1 sine 2 by t only. Okay. What is the optimum value for this B1? Optimum value for B1 is, intuitively we want to know that how correlated the function. It is a sine 2 pi by t. This value is calculated to be, B1 is 2 by t 0 to t f of t, sine 2t by t is dt. So in the sense you want to correlate the function f of t, that means the periodic function, and this base is sine function. In terms of that, optimal value for B1 is given by this integral value, 2 by t, 0 to t, f of t sine 2 by t by t equal to dt. This is a mathematical way of writing the correlation between two functions over the interval 0 to t. The derivation of the factor 2 is known. Why it is coming like that? Right. Working through the mathematics of the above equation, I think why it is not B1 is 2 by pi. When B1, the first two terms from the equation 3 evaluated with the optimum value for A0 and B1. Now we add together to produce, look at this. The same square curve, now it is by means of A1 plus B1 set, the two-term expansion in the Fourier series, now you are getting. So this rectangle form of this curve, it is represented now by means of curve. Now we will increase the term now. A0, AM and Bn. So these are all the called Fourier coefficients. Now you can understand how to calculate the Fourier coefficients. The Fourier coefficient is the function and cos 2 pi mt by t, and Bn is f of t sin 2 pi nt by t. Sir, why you are taking cos and sin? You will know the story behind it. All these represent the correlation of the function f of t with the basis function sine and cos functions. For a specific square wave, as in the figure, optimal value comes out to be A0 equal to half, AM equal to 0 for m equal to 1, 2, 3, and Bn equal to 2 pi by n is odd, and again when n is even, it is equal to 0. Now we have calculated the, of course, there's some integration, calculus, simplification is there, algebraic manipulations are there. After that, you are going to get all these values. Now I'm not doing all these calculations. Believe me that these values are calculated correctly. Note that all of the AM values except A0 turns out to be 0. That means coefficients of cos theta, cos cosine function. The simple reason for this can be found by looking at the function gt, f of t minus A0. Now gt is the square wave with the constant term offset removed, so that the average of the function is 0. It turns out that gt is an odd function and the cosine function all are even functions. So hence all the values of A1, A2, A3 do not contribute gt or f of t, so it must be 0. Why we are getting all the coefficients are AM, IMs are 0. This is the reason. Okay, now you take one more term, 3 terms. 3-term expansion you will get, this curve is approximated by this type of curve when you take 3 terms. Doing all the coefficients you have to calculate, that means A0, B1 and B3, because B2 equal to 0. Okay, now you take 7-term expansion, A0, B1, B3, B5, B7, B9, B11, all other coefficients are zeros. And here, you see, look at this function and you are approximately getting this same function now. So, how approximate? This is what in the image reconstruction you are doing it. If this is the original, by means of Fourier series approximation, you are getting nearly same curve or image. This is the fundamental idea of behind the image processing using mathematical ideas. The most important equation, the formula for Fourier coefficients. These equations give the optimal values for any periodic function. The main point is to understand any periodic function can be represented the sum of sinusoidal functions, each with the frequency with some integer multiples of fundamental period t. Integer multiple inside the cosine and the sine function, and it is multiplied by the frequency, that is frequencies an and bn. So far in Fourier series we have used only real numbers. Yeah. Now in engineering and physics and many applied fields, and using complex numbers makes things easier to understand, more mathematically elegant and beautiful. That means, in other words, complex form of Fourier series. We will go to the previous analysis using the complex form of Fourier series. Instead of using cos theta and sin theta, we will write in terms of complex form. We want to rewrite the periodic function with the period t with the infinite sum of sinusoidal functions, cosine and sine. In this case, we will use the complex exponential function as the basis. What is the basic idea here is, e power I theta. This is equal to cos theta plus I sin theta. Now we know that cos function and the sin function is there. We will write in terms of exponential of I theta. And this exponential, this is called Euler representation, Euler formula. Now, E is a number, it is obtained from infinite series. What is this I? I is a fellow of this complex creature. I is a complex creature, square root of -1. And theta is the angle. Now you are going to have multiples of theta here in our image process lecture. That is, we want to find the coefficient Cn in the following formula. I must tell that what is the formula. Now the Fourier series in the complex form is, I mean, we already used an and bn, therefore we will use now Cn exponential I 2 pi nt by t, n going from minus into plus infinity. So where exponential it is cos t plus I sin t, where I is square root of -1. Okay, now this is a complex form of this. Now we will do some exercise and also we will get the coefficients. From this, how the images are restored using sinusoidal function. From equation 4, the unknown Fourier coefficients are now the Cn, where n is an integer between minus into plus infinity, and Cn is 1 by t, 0 to t, f of t, exponential minus I 2 pi nt by t dt. Okay. Now when you evaluate this, when you find out that the C1 and C2, and therefore one more very beautiful item we are going to see. The above equation gives C0 equal to 1 by 2, Cn equal to 1 by I pi n, where n equal to plus or minus 1, plus or minus 3, plus or minus 5. And for even values, it is equal to 0. That means C2, C4, C6, C minus 2, C minus 4. But whereas here C1 and C minus 1, both are same here. I mean, we are going to see that, how we are going to see. Note that the Fourier coefficients are complex numbers, even though the series is the 4, evaluated with the coefficients in the equation, result in the real function. Now, C minus n equal to Cn. This Cn bar is nothing but a complex conjugate. So, in the following condition, it is true that the resultant function Gt will be entirely real. So, your complex form of equation will become real when this complex conjugate C minus n and Cn are same. Now, you take example 1 to the complex form. Determine the Fourier coefficients, the cosine function f of t is cos 4 pi by t, as shown in figure here. Now, look at this. Cos function, cos 0, here is 0. Cos 0 is 1. Like that, this cosine function is going on. Right? Of course, sine function means it will start from 0. But cos means it will start from 1. And then here also it is reaching there. Okay, for this function, first we need to find out the fundamental period. What is the period here? Since f of t repeats itself 2 times from 0 to 1. Is it so? 0 to 1, it is repeating 2 times. 0 to 1. First time it is coming, second time it is coming. That's what we mean by saying 2 times. So the period is, that means f of t repeats itself 2 times from 0 to t. So the period t is 0 to 0.5. We will find the complex form of the Fourier series. How? Now the Cn is the formula. Using this formula, you calculate Cn equal to, or t is 0.5, 0 to 0.5, cos 4 pi t, exponential, t is here 0.5 and dt. Okay, after evaluation, this gives C1 equal to 0.5, C minus 1 is 0.5, for other values of n, Cn equal to 0. Oh, now we get the complex form of the Fourier series. T comes outside, 0.5, e power I 4 pi t minus I 4 pi t, for this equation. I think you can evaluate this. What is e power minus I theta cos theta minus I sin theta? Therefore, e power I theta plus e power minus I theta by 2, adding both I sin theta will go, 2 cos theta will get, therefore we will get cos theta. Now using this idea, for this function you are getting your original function. So this is the Fourier series expansion for this cos 4 pi t using the complex format. Now example 2. Determine this is, I know everybody knows about this. This is called the SAW function, right? SAW function, that is the SAW used to cut your woods and other things. So for this SAW function, first of all determine the Fourier coefficients. How to do that? The Fourier coefficients are calculated to be 1 by t, 0 to t f of t. Well, here the function f of t is given. What is your f of t? Substituting this and then evaluating this. After simplification, you will get I times a by 2 pi n. That is your Cn. And C naught equal to a by 2. Okay. Now, complex form of now, n equal to, now you take 3 terms, minus 1, 0, 1. Terms give the following function, superimposed on the original f of t. Original f of t is the SAW function. But using for n equal to minus 1, 0 and t, you are getting a Fourier series like this in the complex form. And when you draw the curve, it will come like this. Now, when you increase the more and more terms, it is going to coincide with your SAW function. So, look at this. How many terms you have taken? 1, 2, 3, 4, 5, 6, 7. So, the SAW function is the 7 Fourier coefficient. Now, it is approximately nearing it. Now, when you increase the number of terms, let me see. Now, getting exactly same. I mean, very small variations will be there. Now, 41 Fourier coefficients, when you take it, this is going to coincide with your SAW function. So that is it. So this is the basic idea of in the image processing. Your original image is given by means of Fourier series. You can get after, but provided you should know the periodic function. Periodic function which will represent the image. But who is going to give that? But our image is not known. Whether it is a well-defined one or it is a avasat image, how we are going to find out? That is the big question. Assuming that it is always it start with regular figures and irregular figures we will study via regular figures. Always in mathematics, always you start with the simple things. From the simple things, you will calculate the complicated things. That is why now we are seeing the primitive ideas of image processing. So it is very clear that Fourier series G of t is converging on the original function f of t, which is pretty nice, especially for this SAW function. Now let me go to the Fourier transform. Now we don't know whether all functions will be periodic. I will take the non-periodic. I think some noise disturbance. Please off your mic. Hello? Please off your mic. Yeah. Now, Fourier transform is widely used in analyzing and interpreting signals and images. The tool which converts a spatial description of an image into one term of its frequency components is called Fourier transform. So this is the, now, given a curve, using Fourier series, if the curve is periodic, we can very closely approach the curve, no doubt about it. But when you use the transform, the function is non-periodic. Therefore, now you are writing the Fourier transform, and this Fourier transform, how closely it is. You may not get exactly what, but you are going to see that nearest one. That is the idea of numerical analysis. For example, suppose somebody is first time visiting Chennai, where is LIC building? It is a known building for many people. But the outsiders, they will tell you that it is the next nearest known building. To you go that place, from that building that LIC is next to it. Or Spencer Plaza. Once you want to get the Spencer Plaza, one may point out that you go to LIC building, from there you can see the Spencer Plaza. Like that, when unknown value is known, you from the known value, you can, that is why you have error. Calculated value, that original value, you take the difference, you know that error, relative error, and then frequent percentage, all these things are known in numerical analysis. The same idea is here. Only the, if it is known, your boundaries are known, and these boundaries are approximated by usual, provided your boundaries should have a function. Whether periodic or non-periodic, you should know. If we don't know that, you must resort to numerical analysis. That is what all your image processing software are doing it. But here, known that function, which is periodic or non-periodic, but the function is known, then you can capture the image and very closely you can calculate that, reconstruct the image. But if you don't know the functional, then you have only the image, and then the morning first lecture she was telling different ways from gray point of view, and then how to gray into color. I think either in the Facebook or WhatsApp, a white and black here, by just drawing red lines horizontally and vertically, this drawing that very closely when you observe, then only you can see the lines. And that lines will make it that white and black here in the color image. That is, the red line makes it, she was telling that ratio and other things. Using that ratio, you are getting the color image. This came in WhatsApp or the Facebook quite some time. Through Fourier transform, it is possible to compose a signal by superimposing series of sines and cosine functions. Fantastic. These sine and cosine functions are known as basis functions and are mutually orthogonal. Okay, that sine function and cosine function, basis function and are mutually orthogonal. So why do you want to go this mutually orthogonal component? This is again, for example, now we have a vector V1 of vegetables and vector V2 prices. Now you can represent it like this. A1, A2, A3, for example 3. Now here I am giving in terms of kgs, right? I mean this is half kg and this is quarter kg and this is 3/4 kg. The price is B1 is the price and B2 is the price and B3 is the price. Now what is the total price you want to give it to the vendor? Is nothing but you are going to take what? Pointwise multiplication. Okay. Now let us start our discussion from the kitchen, right? A1 B1, A2 B2 plus A3 B3. So this is nothing but, the dot product is nothing but the vector of vegetables and the vector of prices. When you take the dot product, this much amount you have to give it to the vendor. So the dot product, rather you write this vector A, dot vector B, we call it dot product means pointwise multiplication. If it is finite pointwise multiplication, suppose it is a series. For example, it is A1, A2, A3 like this. If it is a series, B1, B2, if it is a series, Then this pointwise multiplication is known as Hadamard multiplication. This is called Hadamard multiplication. This in complex analysis, people will study about this. Okay, now this dot product, it is nothing but this. Okay, right. Now instead of that, suppose we have f is a function or f1 is a function and f2 is another function. When you take the pointwise multiplication, namely f1 of x dot f2 of x. Now here, earlier, it is going from 1, 2, 3 integers. It is varying over a set of integers. Now, this x is varying over a real line. Real line. Then you take this integration over R. What is this? This is nothing but called inner product. So, the idea of dot product, when it comes to function space, it becomes inner product. Using this inner product, and then Hilbert space is defined and other things are defined, or most general function space. Okay, why I am telling here, when this dot product is going to produce coefficients, Fourier coefficient, for which the orthogonality condition is very, very important. If their orthogonality condition is orthogonal, you are going to get some constant. Otherwise, if they are not orthogonal, you are going to get 0. That means if two vectors are perpendicular, you will get some value. If it is not perpendicular, we are going to get 0. It's a very fundamental vector algebra that we have learned in our high school classes. Fine. Right. Now I'm trying to tell why that orthogonality comes. The transform decomposes the signal into basis functions. Basis functions must be orthogonal, which means that it determines the contribution of each basis function in the structure of the original signal. What is that? That is why these individual contributions are called Fourier coefficients. That's what you have studied AN and BN. In the complex case, it is CN. Reconstruction of the original signal from its Fourier coefficients is accomplished by multiplying each basis function. Namely, here it is cos and sine. You make it more general, f1 and f2, or phi function, pm and pn. Basis function with the corresponding coefficients, adding them together, that means a linear superposition of basis functions. Right. Sorry. Linear superposition of basis functions. Now, the Fourier analysis is one of the most widely used tools in spectral analysis. What is meant by spectrum? Spectrum, you see, I think I'm not going away from this, but I cannot stop telling what it is. For example, suppose you have a line. Yeah. When you multiply this by lambda times here, of course, lambda greater than 1. When lambda less than 1, it will become, again it is lambda x. Then lambda less than 1. Okay? So, this lambda, it is either it can stretch or it can contract. So, that is why if f of x equal to x, a point, and after operating by f, again it is x, it is called a fixed point. But if this is equal to lambda x, that means it is scaling. Scale means it may be expanded or it is contracted. So the same thing in the terms of matrix A, matrix, say for example, x is the matrix, and you take this lambda times x is the matrix. So x equal to lambda times x, that means you are multiplying by the linear transformation. How this x is operated on f is operating on x, like that a is operating on x, lambda times x in terms of matrices. Matrix is a linear transformation. So now this lambda, we call it eigenvalues. Eigenvalues. I mean single word, eigenvalues. So different values of lambda 1, lambda 2, depending upon your dimensionality of x and a. you will get different eigenvalues. Why this eigenvalue? Because rays are coming. These rays are nothing but expansion of the eigenvalues. That is why it is called spectrum. So when a light passes through the hole, you are getting an image. That means it is lambda times x, lambda 1 times x, lambda 2 times x, lambda 3 times x. That is why in physics they are studying it as a spectrum. Okay, now the same idea here. Here you are getting that spectral density f of omega of the time domain signal f of t. So f of omega is actually complex. So one obtains the amplitude spectral density AF and the space spectral density. No, don't bother about all these technical terms. Once you get into it, you will know what they are. But anyhow, this spectral density, the understanding of that spectrum is nothing but the set of eigenvalues. But in function spaces, you are studying the spectrum. Here also you are studying the spectrum. One obtains the amplitude spectrum density AF. And today morning we had that lecture about the spectrum of values explained by Dr. Deepa. Right. Now another way of looking at the Fourier transform is that it answers the question. What question? On continuous distribution of sine waves, AF cos of this, when added together on a continuous basis, best represent the original time signal. When it is going to give that original, we call these distributions the amplitude and phase spectral densities. We call it spectra. Complex exponentials are popular basis functions because in many engineering and science problems, the relevant signals are sinusoidal in nature. Okay. Now it is noticed that when signals are sinusoidal in nature, the wide spectrum of the basis function is needed in order to represent the time signal accurately. Very important property of the family of functions, psi of t, is that it is orthogonal. What do you mean by that? The basis function in the Fourier transform phi of t is e power j omega t or I omega t. J is replaced by I also. So the Fourier transform could be more generally written as using complex conjugate. The test for orthogonality is done like this. Whenever m equal to m, you will get some value k. In fact, we don't know what is that function. Therefore, I'm just putting that k. If the m is not equal to 0, then you will get 0 here. Fine. For complex exponentials, because they are infinite in duration, one ends up with the k equal to infinity. So that should not happen. So therefore, what you are taking is minus t by 2 to t by 2. That means the period is t. So divide by 1 by t and take the average t times infinity. And then same function. So because at some point the function may be unbounded, this is nothing but it will become an improper integral. The improper integral is dealt with proper way. So make it a proper integral and 1 by t. So this is a mathematical trick how to handle improper situation in a proper way. That's what we are doing it here. Now in computer science or in engineering, you should know why we are taking like. What is the mathematical background? What is the mathematical idea? What is the which part of mathematics authorizes you to use this? Why you want to go like this? Because of this improperness in the integral. We have to. That's why in the first year M1 class you are studying improper integral. Improper integral, how you have to handle this? Improper at the lower part, improper at the higher part. I mean top part of the interval. These are all the important ones. Not only their integral limits are improper. Sometimes the functions may be improper. Even functions are improper, how you have to deal with this. So, when this is the integration symbol, here improper may occur, here improper may occur, or both may improper occur. And then here the integrand may also improperness may occur. These are all. These are main. Finest of the fine mathematics analysis will deal with all these things, namely in measure theory. And then how you have to handle this, it's a beautiful theory in mathematics. When you understand this, Then in engineering, then you can apply it. Actually, minus t to 2 t by 2, you can take that, and then you take that average and you are going to get the same value. Okay, fine. Now for complex exponential, this becomes, when you multiply this, it will become like this, and see 1 and 0. So when k equal to 1, the function is said to be orthonormal. You might have heard about ijk function in the three-dimensional space. That ijk vector, unit vector, they are orthonormal vectors. Because when you take that dot product, you will get 1. Fine. Various types of signals can be analyzed with the Fourier transform. How? If f of t is periodic, then the amplitude spectral density clusters into discrete frequencies that are harmonics of the fundamental frequency. This is highly mathematical terms, and therefore you just you know how to calculate the Fourier coefficients. That is enough for computer science people or engineering people. One needs to invoke Dirac delta function if the Fourier transform is used. Otherwise, Fourier series coefficients can be computed and the same result can be obtained. You know, the Dirac delta, first of all, it's not a function. It's a physics people have used this. Then why do you want to study this? At point, it is infinity. At x is equal to 0, it is equal to infinity, and other parts it is equal to 0. That is a Dirac delta function. But the Dirac delta function, it is how we go used to minus t by 2 to t by 2. The same trick is used to study the Dirac delta function. There also you are approximating the Dirac delta function over the interval minus epsilon to plus epsilon and divided by 1 by 2 epsilon. The same trick is used here. Okay. In order to use this, we will use 1 by 2 epsilon, integration going from minus epsilon to plus epsilon, and then delta of that function into dt. This is how you should study, you used to handle this. In physics, they will use it. But mathematicians won't accept this as a definition of a function. Because we never take value of the function at infinity means we simply call it is an undefined. But here in physics, it gives lot of ideas, and Dirac has used in when he was studying quantum mechanics, he has used this function, and that has it has paved way to study many mathematical objects. Even though we people won't accept this as a function at first instance, but we don't know what part of mathematics it will create, and it worked and very nicely done in many parts. For example, finding the roots of the equation. There also we'll use this Dirac delta idea, and you can count the number of zeros of the polynomials also. So in polynomial, number of zeros when you want to count, using Dirac delta function, you can write down the expression. And if you use that random polynomials, you can build that average number of real zeros you can calculate using that some formula. That is a very big story about that is a Dirac delta function. Okay, we will not go to that. F of t is deterministic and discrete. The discrete time Fourier transform may be used to generate the frequency function. Am I exceeding time? Hello?
So, okay, sir, continue, sir.
Okay, thank you. If f of t is assumed to be both periodic and discrete, then a discrete Fourier transform or its fast numerical equivalent, fast Fourier transform may be applied to compute the spectrum. So, as I told you that the spectrum means it is like eigenvalues, that the spectrum here that frequencies, and this you can calculate using fast Fourier transform and a discrete Fourier transform. Because as I told you, you are the original image. That original image you are converting into a discrete part. That means quantifying it. From quantification, that you are converting into digital image. So the digital image can ultimately shows telling that it is only zeros and ones. Like that here, the fast Fourier transform and the DFT, discrete Fourier transform, both are serving that purpose. If ft is random, then in general, one will have a difficult time computing Fourier integral of the random data. So what we have to do? Hence, treat the input as data and use fast Fourier transform for the result of doing so is a random spectrum. As I told you, here, whether it is a periodic or non-periodic, only you know the image. Only that image means that you quantify it and then use this fast Fourier transform. And because you are random manner, you are splitting it and then doing it, therefore you are getting a random spectrum. This single random spectrum can give an idea of the frequency response, and in many instances it can be misleading, definitely. Better approach is to take average of the random spectrum. Now you will understand why we are taking average. Average, that means in probability it is called expectation. Whenever this random data, it will mislead, and therefore you are taking the average of the random spectrum. This lists the formation of power spectral density, which is an average over FFT magnitude spectrum squared. Again, here, why this square concept comes? See, whenever you have, for example, now you have data at different points. Now, what is the closest curve you want to take it? Now, you take this measure. Now here, when you take this value and this value, difference is positive. But whereas here it is negative, here it is negative, and here it is positive. But we know there is a difference, but it is positive or negative. You may square it up, both will go. Therefore, you are taking the errors. Just because you are fitting this line to this data, the errors committed by them, and you are taking the square. That is why you are taking mean square errors, and the mean square error that you want to minimize this. This is the principle of least square concept, which leads to the formulation of power spectral density. Okay, fine. In certain signals, both random and deterministic, we are interested in spectrum as a function of time in the signal. This suggests finding the spectrum over the limited time bin, moving the bin, sometimes overlap, with or without, recomputing the spectrum, and so on. This method is known as short-time Fourier transform or the Gabor transform. Again, it's a transform method. Discrete Fourier transform. It is an estimation of the Fourier transform which uses the finite number of sample points of the original signal to estimate the Fourier transform. Now, this is a computer science point of view. Order of computation is big O of n square. Fast Fourier transform, when you take it, that computation will be capital O of n log n, or because of the similarity properties of discrete Fourier transform. So DFT and the FFT. Now look at this Fourier basis function. This is a sine function. This is again a sine. So you go, that means you are increasing the frequency. Now again you increase the frequency. The input is non-periodic signal. The superposition of the periodic basis function does not accurately represent the signal. One way to overcome this problem is to extend the signal at both ends to make it periodic. This is what I was telling. You study only for periodic functions. Any non-periodic function, you make the function to extend this time axis and then see that where it mixes, make it as a periodic function. That's what it is. One way to overcome this problem is to extend the signal at both ends to make it periodic. Okay? Right. Once it is periodic, you know how to do it. Periodic function means either Fourier series or non-periodic means then you have to go for Fourier transform. Now, you are taking a part of it, part of the function, part of the signal, or part of the image, window function. And this window function and this is a window signal by means of proper transformation. Another solution to use windowed Fourier transform, WFT. So DFT, FFT, and WN. Excuse me. I think I have crossed my limit, I think. Anyhow, discrete Fourier transform. I don't want to just to pull on this. Now I stop with this. For because the time is up, there are actually there are some more another 30 slides are there. It will take another 1 hour to complete this wavelet business. I tell you briefly why wavelet comes into the picture. First of all, first thing, let me review. If it is a periodic function, you can approximate by means of Fourier series. If it is a non-periodic function, you can approximate it by means of Fourier transform. But Fourier transform, we have different discrete cosine and different methods of doing it. If it because it's a periodic, non-periodic function, but therefore you are taking sampling it actually, sampling sampling. Using that sampling means you are discretizing it. From this discretization, you are taking some data. From the data, you are analyzing it. This is what in the image processing you are doing it. Because exact form, whether periodic form or non-periodic form, only you know. What is the shape, we don't know exactly. Right? So that is where you have the Fourier series and Fourier transform. But where the Fourier series form fails is when you take the small, for example, very near to 0 to epsilon, where you cannot apply Fourier transform. It will not give the exact, because when epsilon becomes very close to 0, for example, sine function and the x function both are same. For example, that is the idea of the first um, limit theorem you are studying in your basic classes. Sin x by x, limit x approaching to 0, this is equal to 1. Both are same. Sin function and x function, when x is very close, suppose here, sin function starts here and y equal to x here. So it is a very small sin function and this y equal to x, both are same. That is why it is equal to 1. When x is approaching to 0, both are same. Therefore, but in this place, wavelet concept is introduced in 1960, 1960, and people started studying it. In fact, one of the inventor visited our institute, and then she gave a series of lectures. The wavelet is named after her. I think just for namesake, I will tell that what is her name. Very difficult to pronounce her name. Yeah. Sorry for pushing that slides. I thought of covering these wavelets also. Yeah. Her name is Debussy. This Debussy, there are wavelet named after Debussy. Her wavelet concept has given a very nearly beautiful approximation of original curve. That is what I want to say about wavelet. Of course, there are so many wavelets are available. From 1910 onwards, 1989, you have so many wavelets. Those who find that starting from R function, Morlet wavelet, then Grossman, like that it is going on. Then 1988, Debussy concept, very compact support orthogonal wavelets. This I explained that orthogonality, importance of the orthogonality, because it helps us to calculate the Fourier coefficients. So whenever you define a wavelet concept, that you see that orthogonality concept is introduced, then you will get a new type of approximation to the original image. This is what I want to tell you. Yes. And finally, I thank all the participants. There are beautiful arguments are there. Yeah, I think she has also given the same type. You know what is that girl? It's a Swedish modeling girl, Lena. Yeah, actually, it is spelling is Lenna. We should not pronounce it Lena. It is Lena. Lena's, and by using different transformation, you are getting the nearest picture to this. And JPEG compression, that is what you are using that JPEG files there. Your wavelet theory and other transformations are used. Of course, there are other transformations are also used in image processing. Just I have mentioned Fourier series, Fourier transform, and wavelet. Just I waved my hands without giving much details. And lastly, I thank everybody, those who have participated, and also the organizers. Thank you very much.
Thank you, sir.
Come on. Sorry, I have taken more time, I think. Okay.
Yes, sir.
Okay.
Anybody have any questions?
It is a mixture of mathematics and the computer science. Computer science question means only Dr. Deepa will give answer. If any mathematics question, I can give answer to this. Or just email your queries or references, and then organizers can collect the questions and then forward it to me. I will give answer to them individually.
Okay, sir.
Okay?
Okay.
Okay, sir. Sure.
Thank you very much.
Okay, sir.
Bye.
Thank you very much for your interviewing section. Everyone really liked it, sir.
Uh,
So don't feel bad. It went over the session. We really enjoyed it. It wasn't as if it went for such a
no,
long time.
I want to create a classroom atmosphere. Therefore, I put a green board background. I have given the material.
Yeah, it was very nice, sir.
Thank you.
Thank you,
Ma'am,
sir.
Ma'am,
Yes.
can we go for the valedictory section?
Okay, sir. Sure. Sure.
Now I call upon Dr. P. Mercy, Head of the Department of Mathematics and the Chief Editor of GJAECSMA, to propose the vote of thanks.
A pleasant good evening to all. It is my honor and a privilege to propose the vote of thanks for today's webinar. I would like to thank our webinar speakers, Dr. St. Deepa ma'am and Dr. P. Tangraj sir, for enlightening us with their knowledge. Today's webinar was mind-blowing session. I wholeheartedly thank the speakers for spending time from their busy schedule. Thank you so much. I thank Dr. Behera, Dean of Academic, for his special address. I also like to thank our management, Vice Chancellor, and Register for giving the permission to organize this webinar. A special thanks to Dr. Pradeep Kenny, Head of the Department of Computer Science, Chief Editor, Global Journal of Applied Engineering in Computer Science and Mathematics. He really worked hard to make this event successful. Finally, I thank all the participants for your presence, and it is our sincere hope that the webinar satisfied your expectation. Hope we will meet you all in another webinar in near future. Thank you to all. Dear participants, the feedback form link is displayed in the chat box. Kindly fill it. Certificate will be provided only to those who submitted the feedback form. Thank you, one and all.
One feedback form is not available, ma'am. The link is not available.
Yes, we will send now, ma'am. Wait.
The feedback link will be posted now. It will be available for another 1 hour.
Okay, ma.
Okay, sir.
Okay, I take leave. Okay.
Okay, sir.
Fine,
Okay, sir.
fine.
Thank you so much, sir.
Right. Okay, fine.
Okay, sir.